My name is Bob Bowman. I'm on the board of directors of the Mound Science and Energy Museum Association, and one of my tasks is to coordinate our monthly lectures and seminars. And tonight we're actually very pleased to have Dr. Chad Barkley, who is a former Mound employee. Didn't work for Monsanto, I don't think. You worked actually for Monsanto for a short time before.
For a short time.
And then went to Idaho and now UDRI, and is a knowledgeable expert on radioisotope power system, which is a continuation of course, the RTGs that were invented, developed, and produced here at Mound for well over 30 years. So this is a chance for us all to catch up on what's happened. Let's welcome Chad. Thank you.
Can everyone hear me? Okay, good. Yeah, I don't like standing behind podiums. So I came to work at Mound in 1988, and I moved to the space program and worked for Ed Howell over there, starting in '92 time frame. And so what's funny is I was just talking to Bob, and I was the baby in the group. I was still in my 20s. I was the youngest person in the RPS program, and it's really an honor to be able to keep working in the program, even though it left Mound many years ago. Almost, I guess it's been 20 years ago now. And so the work that we're doing at UDRI is kind of carrying on the tradition of Mound. And I think, you know, one of the interesting things about our experience at Mound is it was a sense of community and family, and there wasn't a problem that we couldn't tackle and figure out and address. In the different places that I've worked, they had the opportunity to work at Idaho National Laboratory that inherited the program, and that culture that we have here is not the same everywhere else in the DOE complex. It's unique, and so as we continue to carry on the tradition of Ken Jordan and John Burden, thank you very much. As we try to carry on the tradition at UDRI of those gentlemen and all of us that have had an opportunity to not only work in the RPS program, but also to work at Mound, you know, we're trying to continue the same culture that we had here at UDRI for the space program. So, a lot of what, who all in here worked in the space program at one time or another when they were at Mound? So there's Joe Miles, there's Bob, Ken, Ed. So some of the stuff that I'm going to present is not going to be new. Some of it will be new, some of it. And if you have any questions, please don't wait to the end. Just go ahead and ask them, and we'll just, I'll address them as we go. So what I'm going to talk about is kind of, I'll start with the post-Cassini mission. So, you know, obviously Cassini launched in 1997. And so kind of what happened to the RPS program in general and RPS designs, radioisotope power system designs, post-Cassini. And then I'm going to transition into conversion technologies to kind of give everyone kind of an update of where we're going with the RPS conversion technologies. And what you'll see, though, is it's kind of back to the future. In some cases, there's things that are new, and other cases that are things that are old that we're making new again. And then I'm going to talk about the RPS technologies in development. So kind of where we're at, what we've done, beyond what you'll see in some of the mission sets, and we'll go on from there to open it up for any questions. So in 2016, Pluto New Horizons launched. It had a general purpose heat source RTG on it, and we'll talk a little bit more detail about that specific RTG. That was the first mission after Cassini, and so if you think about it, it's almost 9 years since the launch of Cassini. And so as you kind of look through the cadence of missions, so you have 2006, 2012, and that was Mars Science Laboratory, which used a multi-mission radioisotope thermoelectric generator. And then, obviously, 8 years later, we do Mars 2020. There's a huge infrastructure that's in place. Obviously, you have Oak Ridge National Laboratory, you have Los Alamos National Laboratory, you have Idaho National Laboratory, and in today's dollars, you're looking at about $100 million a year to maintain that infrastructure. And what NASA charges missions that intend to use an RTG is about $55 to $60 million for the mission. So you think that over a 10-year span, that's a lot of money that NASA has to invest just to kind of keep the lights on. And you'll see that on the DOE side of the house, sometimes we don't always fulfill our mission requirements, and we'll cover that here in a few missions. So the next mission that's due to launch is, again, you see it's about a 7-year cadence, is Dragonfly. And I don't know if anyone's heard about that. And again, we'll cover that particular mission here in a few minutes. But that also will have a multi-mission radioisotope thermoelectric generator on it. And I'll describe a little bit more what some of the differences are on that RTG compared to the Mars 2020 and the Curiosity rover RTGs. Then I threw this other slide up as kind of just something to kind of get the juices flowing a little bit. So what are some other potential RPS missions moving forward? And so I list 2 up there. One's called Strat5. And that is it's a TBD mission, so there really isn't a design mission set yet, but there is a requirement. And so there's actually a commercial endeavor. So much like we have SpaceX and Blue Origin and other commercial launch providers besides just NASA, there are now coming into the industry commercial entities that want to build RTGs. So we'll talk a little bit about that, and we're doing some work at the University Dayton Research Institute to support some of these commercial endeavors. And then there's a NASA mission called Tipping Point, and that's, again, a to-be-determined commercial lunar mission. And the idea there is taking americium-241, developing an RTG concept, kind of a plug-and-play technology. So the heat source itself could be used in, say, a communications node, could be used in a rover, could be used for a science experiment. And if everyone remembers SNAP 27 from the Apollo era, you know, essentially with Apollo 12, you saw an astronaut pull out the heat source from the LEM and then actually stick it into the RTG. Kind of in a more evolved version of that, but it's the same kind of idea moving forward. So, what was the first mission beyond Cassini? Was Pluto New Horizons. That was powered by one GPHS RTG. That was F8. That was the last flight unit that was made. Out of the series, there were 7 used before it. I think 2 on Galileo, 1 on Ulysses, 3 on Cassini. And then we had F5 as the flight spare, and then we had F8. And Ed, I think you were out in Idaho for some of that, correct? Yeah. So if you notice, generally for a GPHS RTG, the beginning of mission power, in the beginning of mission, so we have beginning of life, which, you know, after it was fueled here, that would be beginning of life. Beginning of mission is actually once it gets on station. The beginning of mission power is a little bit lower than what we'd expect for a GPHS RTG, and that's mainly because DOE couldn't produce enough fuel clads to power GPHS RTG. So there were 20 new fuel clads, and then they took 52 older fuel clads from the F5. So at Idaho National Laboratory, they defueled F5. They pulled the gizzes out and then installed them in new module assembly hardware, which was updated for safety purposes. And then with the new fuel clads, they were able to go ahead and fuel that. And so what we ended up with was a less than optimum power requirement, but sufficient enough for the mission. And as you can see here, this is down at Cape Kennedy. This is actually F8, where they're doing a test fit in PHSF, which is the Payload Storage Handling Facility at Kennedy Space Center. They're doing a test fit and powering up the spacecraft for the first time. And then, as you'll see in a couple slides for Curiosity, they'll demate the RTG, go ahead and install the spacecraft into the payload, and then put the fairing on. And then once everything is set up on the launch pad, the RTG is actually taken up to the VIF, the Vehicle Integration Facility, on top of the launch pad, and then integrated there to the spacecraft for the last time. Just a little bit of trivia, NASA's actually getting away from that. On all future missions, the RTG will be permanently mated to the spacecraft in PHSF like you see here, and then the whole kit and caboodle will be integrated onto the launch vehicle, and then the payload fairings put on, and then that's the new integration technique. I'm not exactly sure what the rationale is behind that, whether it's a safety issue or something else, but it's just a little bit different way of integrating the RTG than what's been done historically. And just to kind of, and I don't intend to go into any of the mission profiles per se, but I think it's kind of interesting. You know, the actual encounter for this was a very short period of time. It was only about a 6-hour encounter. So it was a flyby through past Pluto and its moon Charon. And so the spacecraft actually flew and then turned around so it could get pictures, and then had to turn around again to send all the telemetry data back. So as it flew past Pluto and Charon, it was able to capture some really amazing images, which I think is quite impressive when you're shooting something all the way out to Pluto to make sure that you have a rendezvous and be able to actually, you know, pinpoint where you need to be able to start the encounter and actually get good science. And then obviously after that, it flew into the Kuiper Belt, and then it did image a few Kuiper Belt objects. And so it's continuing forward, but I don't think that it actually has a real mission beyond that. The next mission, which was launched in 2012, was the Mars Science Laboratory. You can see here, this is actually an artistic rendition of the landing of the rover. I don't know if you guys are familiar with how that rover actually landed. So think of it as kind of like the LEM from the Apollo missions coming in and starting to land, and then it actually drops the rover down from it, cuts the cables, and then flies off and crashes, which I think is rather a unique delivery system for this particular mission. And what's complicated about this from an RTG perspective is when it's all tucked up into the spacecraft itself before launch, the hydrazine tanks for that descent stage are right there next to the RTG. And so what they have to do is artificially cool the RTG to make sure they don't overheat the hydrazine tanks during launch. And so there was some special accommodations made to that particular RTG and some additional testing that went on with the individual fuel clads that were inside the RTG to ensure that if there was a launch accident, because they were artificially cooling them to about 700 degrees C. Normally the centerline temperatures of those clads are significantly higher. They're probably right around 1100 degrees C. So they actually were cooling them quite a bit. They wanted to make sure that the iridium alloy that was there encapsulating the plutonium-238 actually retained its ductility at those temperatures. So there was a number of accommodations made. On this particular mission, it was one MMRTG. It had a beginning of mission power of 115 watts electric, and had a thermal output just below 2,000 watts. And it used 32 new fuel clads made by Los Alamos National Laboratory. What's interesting about this RTG, as you can see here, it's smaller, obviously. Its specific power is significantly less than a GPHS RTG. It has a separate heat source cavity from the thermoelectric cavity. And if you look at it, it looks kind of vaguely familiar. And I think I covered this on my next slide. No, I don't. I do cover it in a few slides from this one. Obviously, this is really a takeoff from SNAP 19, which was used on the Voyager missions back in the 70s. So if you think about, oh, well, we're developing a new RTG. This one was intended to replace the GPHS RTG, but its specific power was less. It's multi-mission because it could be used on a planetary surface, or it could be used in deep space. It could be fitted with a PRD if it was a requirement. But you know, in the big scheme of things, it is a much less efficient unit. It's using TAGS 85, which is a material. It's a lead telluride on one leg and tags on the other one. I'll cover that in a few minutes. But it's a much less efficient thermoelectric than the silicon germanium that was used in the GPHS RTGs. So here you can see Mars Science Lab. You can see where the RTG is being lifted up to the VIF in what we call the gorilla cage. It used to be the old shipping package for the GPHS RTGs until we got the 9904 shipping package, which was a DOT certified shipping package, whereas this was not a DOT certified shipping package, but still used in the complex to transport the RTGs from one place to another in a non-over-the-road transportation type of setup. You can see here what I was talking about earlier. There's an opening in the payload fairing, and then the RTGs made it to the spacecraft inside the VIF. And then obviously once everything's made it up and everything's electrically checked out, they'll go ahead and put the door on the payload fairing. And then here you can see the launch of Mars Science Laboratory. Of course, the next mission is Mars 2020. What's interesting, I showed you earlier for Curiosity rover, kind of the image of the artistic image, if you will, of the rover being lowered to the surface of Mars. With Mars 2020, they were able to fit it with some extra cameras and whatnot. And you can see here the actual image of the rover just before touchdown on the surface of Mars. So with this particular MMRTG, one of the things NASA wanted to do for this mission is they wanted to make it almost a carbon copy of Mars Science Laboratory. And so you can see here for MSL, they had this Titan launch vehicle, and they used the same one. They used the last one. They had bought it early on with the intent of using it for Mars 2020. I'm going the wrong way. The intent of using it for Mars 2020, and they kept it in storage because what they didn't want to do is have any major configuration changes so that way they can keep the cost down. So as you can see here, the MMRTG is identical with the exception of the beginning initial thermal output is less. Once again, because they had to use, they can only make 16 new fuel clads, and then they had to use 16 older fuel clads that were from a different project that was canceled. So again, maintaining the necessary inventory of plutonium-238 and being able to encapsulate it and get it into a unit. And Ed, do you remember during Cassini, we had 72 clads per RTG. We had 3 RTGs, and Los Alamos was sending us clads weekly almost. They were coming in dribs and drabs, but they did it. And now you can see here, in between Mars 2020 and Curiosity, 8 years, they could only produce 16 new fuel clads. So here we see the MMRTG after it's been still in the base of the gorilla cage. It's up in the VIF and getting ready for integration into onto the spacecraft through the payload fairing. And here you can see the launch of Mars 2020. So the next mission that's on the books is the Dragonfly mission. And has anyone heard about this particular mission? So it's a quadcopter, but it's the size of the Curiosity rover, and the Curiosity rover is the size of a Volkswagen. So it's a pretty interesting mission. The reason why we can do this is obviously Titan has a methane atmosphere, so it's a lot denser atmosphere, and the gravity of Titan is a lot less than Earth, and so it allows us to come up with a mission. And so there's a little bit better picture of the quadcopter. It will have also one MMRTG, but what you can't really see is on the back. This is where the MMRTG goes. But because the surface temperatures of Titan, which is Saturn's moon, one of Saturn's moons, because the surface temperature of Titan is so low, you can't have these radiating fins actually wicking heat out because it would cool the unit too much. And so this on the back is actually an insulated enclosure for the MMRTG, and then they're going to remove the fins on it. And then you can see here in blue, there's some cooling tubes. There's going to be additional cooling tubes added. And so the reject heat from the MMRTG will actually be circulated through the spacecraft to keep it warm. So again, right now, obviously the estimated beginning of mission power is 110 watts electric. And that's after it's been decayed because of the flight time from Earth to Titan. And then the beginning of mission thermal output, once it's on the surface of Titan, is estimated to be just a little under 1900 thermal watts. This is kind of the projected flight plan. As you can see here, it starts off with Earth. There's a few gravity assist maneuvers, and then it takes, launch is supposed to be in 2026, but I think that's actually going to get pushed back to probably 2027 or 2028. And then the encounter will be during landing somewhere in right now projected for 2034, probably really be 2035, 2036. It's just enormous amount of time to get there. And what happens though is, you get a decay of the plutonium-238, and then you're obviously beginning of mission power. Once you reach the surface of Titan, is going to be a little less. So you can see kind of the entry, descent, and landing profile. The spacecraft will enter Titan's atmosphere, much like Curiosity. In this case, the quadcopter will eject from the bottom and then actually start to fly and then land on the surface of Titan. And then during this descent stage here, it's going to be imaging where is it going to go next. And so once it sits down, all of the batteries will recharge off of the MMRTG, and then it'll take off to go to its next mission. And as it's flying to its next destination, there's onboard cameras looking at where am I going to go next, and then they're just going to hop around Titan. And then for every flight, there'll be a separate computer that figures out what's going to be the flight plan for the next mission. Kind of interesting because the time lag between here and Saturn is so long. I want to say, I think it's about 2 hours, if I'm not mistaken, in terms of the speed of light, so how long it would take for communications to get back and forth. So this has to be designed to be completely autonomous. So I'm going to move on to RPS conversion technologies, because really that's kind of where the rubber meets the road. Yes, we have some RTGs, but it's these technologies for how do we convert thermal energy to electrical energy. That's where kind of the rubber meets the road. Obviously this is not a radioisotope power system. This is actually a fission-based power system, but I thought the image was kind of cool and gets the point across. There's actually for this concept, this is called kilopower, and it was a concept developed up at NASA Glenn. And it's basically a small reactor that's buried in the ground. This particular reactor is using HEU, highly enriched uranium, which obviously that's really not going to fly, no pun intended. So they're looking at variations of this concept using high low enriched. It's HALEU, so highly enriched low assay. That's what it is. High enriched low assay uranium. So, and what you see here in these little canisters, those are actually Stirling converters. So basically the reject heat that's coming out of the reactor gets converted to from thermal to mechanical to electrical power here, and then that could power whatever's on the surface. So for the GPHS RTG, it used silicon germanium as its conversion technology. It was developed in the 1960s by RCA Corporation, and the initial production of these couples was at the Harrison Laboratories run by RCA. And those unicouples were used for Voyager 1 and 2 and the multi-100 watt RTGs. And I think the multi-100 watts were on some other missions as well. I don't think these were the only ones, but it was the only NASA ones, I believe. What's interesting now is that going into the GPHS RTG, production of these was reestablished at Lockheed Martin at Valley Forge in the early 1980s. And then obviously those couples were used for Galileo, Ulysses, Cassini, and Pluto, and Horizons. And then production was terminated in 1998. I can't tell you exactly when, but it was in 1998 when that occurred. And we'll talk about this in a few minutes. What's interesting, though, is we're trying to reinvent this technology. Right now, Aerojet Rocketdyne and Teledyne Engineering, which for those of you that weren't affiliated with the space program, we basically had You had Teledyne Engineering kind of did terrestrial units. They used basically the same types of thermoelectric materials that were used in the MMRTG. And then we had Lockheed Martin that did space. And so now we've kind of come full circle. Now we have Aerojet Rocketdyne and Teledyne Engineering making, or attempting to make these thermoelectric couples again. And I'll talk about them in a few slides. On the MMRTG, we had lead telluride, which on the P leg and on the N leg we have tags, which is tellurium, antimony, germanium, and silver. Again, this was a technology developed in the 1960s by Teledyne Energy Systems. And the way that they pack these together, they're closed packed arrays inside of modules. You have 48 of these couples in each module. And then you have 16 of these modules in each MMRTG. Again, the technology was flown for the first time on SNAP 19s, on Pioneer 10 and 11. And of course, now it's currently used on MMRTG. So if you look at the technology, really up to this point, all the way up to Dragonfly to 2027, the technology we use is really from the 60s, all of it. There's really not been anything new that's been developed per se that's flown or is qualified to fly. One of the other technologies that's been going on in the background for a long period of time is the Stirling, which is a free piston engine technology with an integral linear alternator. NASA Glenn has been playing around with this technology since the 1970s. But it really kind of got some traction after the silicon germanium line at Lockheed Martin was shut down. And some, you can kind of look at that, some of it was intentional because really NASA wanted higher efficiency conversion technologies. So obviously, we look at MMRTG, it's a less efficient, so it's somewhat ironic, but it really paved the way for NASA to really start funding these efforts. And in 2003, there was a contract led out of NASA Glenn to develop an 80-watt electric Stirling generator. Ultimately, and we'll cover it in a few slides, ultimately they were able to design and start fabricating a couple of these engineering units, as you can see here on the right, where there were two Stirling converters and then you had a GPHS module on either end. So the problem with this is the controlling the phase, and I'm not showing the controller box here, but controlling the phase, because you can't really use this in a space mission, because if one of those engines starts to get out of phase with the other, you're going to have all kinds of vibration, all kinds of other things going on. The real issue with these things was reliability.
The resonance is mechanical in those.
I'm sorry?
The resonance is mechanical in a free piston Stirling engine.
Yes.
So generally, but if you have a seal failure or something, you get dragged, she'll come off phase and then she'll shake.
Yeah, and so what happens is, and what I didn't really talk about is, in these engines, right, so cryocoolers have been around for a long time, and they'll run, for hundreds of thousands of hours. But if you start to really if you want to run them in reverse, and to go from a cryocooler to a Stirling engine, and you want to get high performance, you got to get the tolerances way down. And so inside these things, the tolerances are micron level tolerances. And so you get any distortion due to thermal expansion, anything that takes any of these components out of whatever their true design geometries are, you start to get internal rubbing and all kinds of other things start to happen. So there's all kinds of bad things that happen when these run. So
mechanical.
Oh yeah. So one of the things that NASA was trying to do is they were trying to come out of the gate with a Ferrari. That's the analogy I like to use, rather than to start with like a Chevrolet, right? Like maybe a Vega or a Chevette or something like that. No, not even a Corvette. They came out of the gate trying to get a Ferrari, and ultimately that kind of spelled the doom for the project. So what I show up here is actually a real honest-to-God Stirling generator that was built for this program. You can see one of the engineering units that was here, tested up at NASA Glenn. In 2006, NASA baselined the ASRG, the Advanced Stirling Radioisotope Generator, for an integrated flight project. So from 2003, they went from concept development to 2006, let's fly this thing. And they were trying to baseline it on a 2016 Discovery class mission. Lockheed Martin Valley Forge was the system integrator for that. So we've gone full circle. So now we have Teledyne, making space RTGs, and now we have Lockheed Martin doing some Sterling work, which actually is a bit ironic because Teledyne Engineering had done some Sterling work in its past. So to me, it seemed like that would have been a better fit. But Lockheed Martin took over because they had no space. They had no space program. GPHS RTG was canceled. They had nothing left, and so to be able to keep them afloat, if you will, they got the contract for ASRG. The design focus was really on reliability and trying to understand there was no mission set for ASRG. So they came up with essentially a bunch of notional mission requirements in terms of performance, system operation, and then they were trying to build a unit to those notional requirements. Long story short, DOE terminated the program in 2013, and basically all work at Lockheed Martin was culminated after that, and anything radioisotope power system related at Lockheed Martin was gone, never to return.
But that was the old GE facility, right? So you had the turmoil of GE shutting down and Lockheed taking over. And
yeah, but that, I went to that facility a few times, especially during the ASRG program, and that was a flourishing facility because they had a lot of weapons work. They had a lot of stuff going on in there.
Yeah, it's a reentry division. They did a lot of the heat shields.
So they had a lot more than just the RTG stuff or RPS stuff. It was really a small portion of that. But all that work is gone, never to return. So all of the equipment that was there, all the hardware got shipped to, we got some of it, JPL got some of it, Idaho got a lot of it, and obviously that'll come into play here in a few slides, but yeah. So everything ended with Lockheed Martin and the space program for radioisotope power systems anyway, 2013. So JPL in the background is always, they're always developing something. So they developed a Scudderite technology. So it's a new type of thermoelectric. And in 2013, NASA initiated the Scudderite Technology Maturation Program. So we just call it STM for short. And the idea there is to take these materials and take multi-mission RTG and essentially retrofit these SKD thermoelectric couples for the TAGS 85 couples, and then thereby getting increased power output. And the way that they named this was enhanced multi-mission, so then you get eMMRTG as opposed to just straight MMRTG. So that contract was let with Teledyne Engineering, essentially reporting to JPL. So the money flowed from NASA RPS program office to JPL to Teledyne Energy Systems. And the goal was that there'd be a 25% beginning of mission power. So instead of starting off at about 120 watts electric, you're around 150 watts electric. And thereby, when you get to your end of design life, which is 17 years, you still have a lot more power. Long story short, the problem you run into is that there's a number of exotic materials or segments in these thermoelectrics, and there's a number of exotic materials that are metallization layers, and they were using zirconium. And I don't know if anyone knows anything about zirconium, but it likes oxygen. It's a getter. And so in the thermoelectric cavity of this, because it's two cavities, you have a heat source cavity and you have a thermoelectric cavity, and there's a lot of insulation in there. Insulation has a lot of moisture in it. And so what was happening is when they were doing their testing for developing this material, it was all done in vacuum. When they actually put it into an MMRTG-like environment, the couples fell apart. So then they went through an exhaustive campaign to figure out other metallization layers that they can put in these different segments. It got to be where I think in each one of these legs there was probably somewhere between 7 and 8 different segments. So you had all these different metallization layers because you had to have compatibility with all these different metals, and then you'd have essentially Kirkendall voiding, which is where you get atoms flowing in one direction and atoms flowing in another, and if you get more going in one direction than the other, you get voids, and then wherever you get voids at these interfaces, then you start to get cracks forming, especially when you thermal cycle them. And long story short, the technology didn't really work out, and the project was not funded after fiscal year 21. So I think, and there's no quote on this that I've read, but my guesstimation is that somewhere between $50 and $100 million was spent on this project. to yield nothing. So we have 2 failed programs here. You got this one, which probably was, I'm guessing, probably somewhere in the same ballpark of $50 to $100 million was spent on that. Another $50 to $100 million spent on this, and it didn't bear any fruit. And so in the background again, one of the things that JPL has been working on is lanthanum telluride as a upgrade for silicon germanium. It does have a fairly high ZT value at 1,000 degrees C, which is about the hot side operating temperature for silicon germanium. Again, notice the same number, about a 25% power increase, a promise of 25% power increase over silicon germanium. And there has been a lot of extensive testing going on at JPL. So we'll move on into what technologies are in development. So we talked about the thermoelectric conversion technologies, and that plays into, obviously, what are some of the other technologies that are going on. This is just an artistic rendition of a cutaway of a 2-module MMRTG. There's a desire by NASA to have small-scale units, anything from about 10 watts electric all the way up to 100 watts electric. And right now we only have an RTG, a flight-proven RTG that's only going to give you, at beginning of mission, around 120 watts electric, as opposed to where the GPHS RTGs were, which were closer to 300 watts electric. What you see here is the University of Leicester in the UK. They are doing development work to design and fabricate an RTG for the European Space Agency. It'll be fueled on americium-241. This is one of their earlier concepts. It's using bismuth telluride, which is a very low efficiency thermoelectric material. It uses bismuth telluride as its thermoelectric conversion technology. But one nice thing about that is it runs at fairly low temperatures. It doesn't degrade, so you don't have all of the degradation of the thermoelectrics in addition to the degradation of the radioisotope. Americium-241 has a 432-year half-life, so for the duration of any mission, it's almost like a constant heat source. And then, of course, what you see down here is kind of, you saw it earlier in one of the earlier slides, it's just a cutaway view of a ASRG concept. Here you can see the controller box. So that's the other difference of this thing. It's not just a plug-and-play device. You have to have a controller box along with it to control the engines, especially during launch, because these things can't be running at real high, at high frequencies during launch because of the vibrations and everything will throw them off. So what they try to do is slow them down during launch to where they're functioning, but they're not running at high speed. And then once they get actually into orbit or wherever they're going to go, they'll start to rev them back up again. So the technology's in development. So the next gen RTG is the next generation RTG that's in development. If you look at it, it looks an awful lot like the GPHS RTG, and there's no, it is not a coincidence. Obviously, this is an earlier rendition. The ones now, this almost looks like an MMRTG on steroids, but right now, Aerojet Rocketdyne is under contract to do what they call build to print. So they have all of the Lockheed Martin prints, as does Teledyne, and they're actually building everything exactly as it was from Lockheed Martin. And so what's interesting about that is a lot of the processes that were used back in the 80s and 90s don't exist anymore. And so they have to either recreate the processes from scratch, or they have to find new modern day processes and demonstrate equivalency for how these things are fabricated. So, and here's where it gets fun. So they have 3 versions of this. Mod 0. Mod 0 is the refurbished F5 RTG. It's a risk mitigation plan in the event that a mission wants a GPHS RTG and we're behind schedule on what they call Mod 1, which is essentially one built by Aerojet Rocketdyne and Teledyne Engineering. We're gonna fly the flight spare for Galileo, Ulysses, and Cassini, and Pluto and New Horizon. Well, Pluto and New Horizon wasn't the flight spare because it was actually defueled. And so, unfortunately, when Idaho National Laboratory defueled it, there was some issues where there was damage to the moly frame, which is on the inside of the RTG, and 7 of the thermoelectric, hot shoes on 7 of the thermoelectric couples were also damaged. So there's a lot of work going on right now at Idaho National Laboratory and throughout the complex to determine whether or not the F5 RTG can be repaired and retrofitted. And what's happened over the years with GPHS RTG, they had 18 GPHS modules in them. The MMRTG has 8, but it has 8 step 1 modules. And so the step 1 modules are just a little bit bigger. They're not taller, they're just a little bit bigger to accommodate some extra material on the inside of the module to make it more safe during, say, a launch accident or a reentry scenario. Step 2 modules are not, also have that design modification, but now they're also taller to make them additionally safe. So what happens is if you're going to do a build to print GPHS RTG, you can't stick 18 step 2 modules in it. You can only stick 16. So right off the bat, you're not going to get the power output from a Mod 1 next-gen RTG. So back to the Mod 0 though. So what they're going to do is accommodate 16 step 2 GPHS modules into the F5 RTG. What they would do is modify essentially the pressure plates on either end and the mid-span support plate to make them a little bit thicker so that you can accommodate 16 modules in a GPHS RTG. And instead of having 290 watts at beginning of mission, you're going to have something around 240 watts electric. So that's an estimate. And that's accommodating for essentially reductions in power output due to those 7 broken couples. So if you look at Mod 1, again, a build to print GPHS RTG, it's again only going to be able to accommodate 16 step 2 modules. So what you have is you have 572 unicouples in a GPHS RTG, and so since you have less of a thermal payload, what that really means is that the hot side temperatures of your 572 unicouples is going to be less. So what you have to do is figure out, do I accept that trade-off, or do I reduce the number of unicouples to 512 to be able to maximize, to get the hot side temperatures where you want to be able to get the maximum power output from the unicouples that you do have. And so there's a lot of work going on right now to determine what's the optimum design changes necessary for a Mod 1 Mod 1 next-gen RTG. Again, Aerojet Rocketdyne is the system integrator. Teledyne Energy Systems is actually going back and recreating all of the processes necessary to make a unicouple. And interestingly enough, we are buying silicon germanium, doped silicon germanium from RGS development in the Netherlands. So we don't have the capability of making the material here in the States. Oak Ridge National Laboratory has made some material, but it's not a really an ideal situation where you want a national lab being your production source for specific materials for a flight mission. Again, we're looking at a beginning of mission power of about 250 watts electric. So this is the next generation, and we're not as good as the last generation, right? So, and so that's due to be completed with an engineering unit ready, and maybe a first mission around 2028. I suspect that could get pushed out a little bit further. And then Mod 2 of that is a retrofit of these, let me go back, of these lanthanum telluride thermoelectrics. Basically, much like what we talked about with EMMRTG, where you have these thermoelectrics that you're going to retrofit into an existing flight configuration. Mod 2 is essentially doing the same kind of thing, but using these lanthanum telluride thermoelectrics, and that would be ready sometime in, quote, the early 2030s. Again, it would involve JPL and Teledyne Energy Systems, which is the winning combination from EMMRTG. And again, everything else would be the same, but here an estimated 400 watts electric. I'll believe it when I see it. So now we're back to dynamic conversion again. Even though ASRG was canceled in 2013, there's still an ongoing need for dynamic radioisotope power. There were 4 contracts cut by NASA Glenn, one to Creair for a turbo Brayton concept, one to Northrop Grumman for a thermoacoustic concept. We had another one from American Superconductor for a Stirling converter, and then again SunPower, which was the contractor that was building the converters for ASRG, is also in the mix. And then there's the European Space Agency. I talked a little bit about this a few slides ago. Their goal was basically to independently design and build an RPS system that puts out 10 watts electric with 200 watts thermal. They've got 12 fuel clads. They are fueled with americium-241 sesquioxide, so AM203. There is some other materials, a little bit of depleted uranium that's put into the material as kind of a microstructural stabilizer so that you don't get the further reduction of AM203. It keeps it kind of in the same phase, so you don't have any phase changes of the material. The primary development activities are really the americium-241 isotope production. That's happening at the UK's National Nuclear Laboratory. And they're looking at that because they have a lot of spent fuel rods that they can go ahead and extract americium from, just kind of milk it out of the fuel rods. And so they've got a process they've stood up. They've demonstrated a bench scale setup. They're working on a pilot scale, and then we'll be going into full-blown production by around 2028. They're also using platinum rhodium encapsulation technologies. Our lightweight roos, which this kind of looks like a lightweight roo, and it's their version of a roo. And the similarities are not coincidence. I mean, they have learned from our designs. They use very similar materials, but instead of using platinum-30 rhodium that we use, because essentially the temperatures for their fuel is less than what it is for 238, they're using actually platinum-10 rhodium. They've done a lot of work. We've done a lot at UDRI. We've done a lot of the high strain rate testing to demonstrate that the performance of that material temperature, and then we've also done impact testing of their non-radioactive fuel clads and RU hardware. So basically looking at different orientations, different impact velocities, and different impact temperatures as well to kind of fully characterize these designs. And then again, their conversion technology, they're looking at 2. The primary is bismuth telluride, which is going to get you your 10 watts electric, but for larger systems, they're also looking at Stirling generators. And so there's been a bit of a collaboration in a sense between NASA Glenn and the University of Leicester on some of their applications of their RTG. So I don't have one here, but if you could imagine a couple of the Stirling converters that I showed in an earlier slide, kind of fitting into this RTG where the fins are, gives you some idea of some ideas that are being conceived. One of the things that NASA Glenn had us do a few years back was when EMMRTG was starting to kind of ramp down and they realized that that wasn't going to be an available flight unit type design, they had UDRI look at, is it possible to take the MMRTG concept with its thermoelectrics in it and then cascade a second stage of thermoelectrics on the outside, not so much the inside, because they didn't like the idea of introducing different materials into the thermoelectric cavity, but can we do it on the outside of the unit? And this is kind of a rough schematic of what that looks like. And so the design concept that we came up with was a housing that had no fins but flats on it. And then you would have thermoelectrics bonded to these fins that would essentially get bolted onto the side of the housing there, and you would have a second stage thermoelectric. The problem with bismuth telluride is you need about a 200 degrees C delta T to get the maximum amount of power output. And so if you're going to try to achieve that, you have these fins that are gigantic. I mean, probably 3 feet in diameter. This unit just becomes unwieldy and large. And so if you can fit more thermoelectrics on here that are actually producing a little less power with a little bit lower delta T. And that's the kind of the concept that we looked at. And so we estimated that the beginning of mission power would go up from about 120 watts electric to 140 watts electric. So a gain of about 20 watts electric. Same thermal output with 32 new fuel clads. What we're looking at is a total on the housing. We would put 360 bismuth telluride modules on that housing. And so what happens is that takes your mass up from about 50 kilograms to almost 100 kilograms. So you're almost doubling your mass by adding all this additional hardware on the outside, the flats plus all this additional thermoelectric hardware. The fins are a little bit different geometry. So your specific power almost gets cut in half. So this thing becomes a flying pig essentially, because so I'm not sure that, you know, NASA's always concerned about mass, because mass is money when you go to launch it. I will say this though, Matt, if you're going to launch on a Falcon 9, people seem to be a lot less concerned about mass than they used to be, because the cost to actually launch something is significantly less than it was if you were doing a NASA mission. But at the end of the day, I mean, you're talking about a 35 to 40% reduction in specific power. Yes, you gain some wattage, but you know, is the juice worth the squeeze? Probably not, because we never got any more funding to do anything else with it. So, as we near the end, so here's where I think things get interesting. I talked earlier about StratFi concepts and tipping point. And so we've been working with a commercial startup that has right now 2 DoD contracts and high probability to get a 3rd NASA contract. And I can't really disclose who they are, because they like to keep their IP really tight. In our community, you know, it's all about showing what you've done, presenting everything so that it's very open source. The Brits do it. We've done it historically, but these commercial entities are really concerned about the IP that they bring to the table, and they don't really like to share. So these concepts you see here, and I'll walk through them, they are just kind of phantom concepts, because I'm not really allowed to show the real ones, but they're close, and I can walk through some of this. So one of the highlights is to demonstrate a non-plutonium-238 RPS. NASA is super excited about that, because it gets them away from having to depend solely on the DOE infrastructure. And the cadence of missions, like I said before, is about once every 7 years. And so if NASA has, much the same way they call them CLPS providers, the Commercial Lunar Payload Service Providers. So if NASA wants to, say, put this water bottle on the surface of the moon, they'll put out an RFP to these CLPS providers. It's Blue Origin, Intuitive Machines, SpaceX, and there's, I think, Sierra Nevada. There's, I think, a handful of other contractors. And they say, I want to put this bottle of water on the moon. And all the CLPS providers, they either independently come provide proposals, or maybe they team up, and they come back and they say, well, here's what we're going to do, and it's going to cost this much money, and we'll do it by this time frame. And NASA goes, okay. They don't care how they do it, right? They think it's a new kind of paradigm shift. They think of it as kind of like UPS. Like, if you're sending a UPS package someplace, you really don't care if it goes by truck, if it goes by plane, if it goes by, you know, it doesn't matter. As long as it gets there by a certain time and it's undamaged, that's all you care about. And so they're thinking these CLPS providers much the same way. And so when we start talking about these commercial space companies for RTGs, you know, NASA's like, I don't care what kind of isotope it is, as long as it puts out 10 watts and you can prove that it's safe and it works, they're happy. And so 10 watts is kind of just the entry level you know, buy-in to this kind of concept. Obviously, the idea would be once you demonstrate something small, you figure out how to make it better. So right now, UDRI, we're actually the design agency for these. We set up a space power assembly facility, so it's kind of a little bit like Lockheed Martin. We're doing design, we're doing assembly, we're involved in launch safety from a testing perspective. So the same kinds of things we're doing with the Brits. We have our own vibration shaker table, so we can check everything through vibration. We've got all the computer simulations for thermal. We've got the computational fluid dynamics stuff, so we can look to see how these things perform in a reentry or a launch accident type scenario. And so our 10-watt design, here you can see, I'm sorry it's difficult to see up here, it has an integral heat shield, and I'll tell you why here in a few seconds. And it's a very small encapsulated, it's about yay big in the big scheme of things. And it has 1 to 4 fuel capsules in it. And so, and those are going to be strontium-90. And now, anyone in here know about strontium-90? Yeah, it's a beta emitter, right? But it puts out you know, a bremsstrahlung that is ungodly. And the problem that we have, all the strontium-90 in the United States is old. It's probably 35 to 40 years old. So, you know, the highest assay you'll have of strontium-90 is about 55%, because you've still got all the other strontium stuff in there. This stuff that we're talking about that's left over from DOE is about 15 to 20% assay. So what happens is, to get the thermal load you need, you have to have a lot of this stuff. And shielding it becomes a real problem. And so if you're under a mass constraint for your RTG, say 50 kilograms, you have to sacrifice something, right? So you sacrifice shielding for mass. And so then you have to figure out, how do you fuel this thing remotely with manipulators? And so we have manipulator stations where we're actually figuring out how to design manipulator-friendly attributes into the design so that it can be fueled, and it won't be fueled here, but so that it can be fueled by somebody with strontium-90. And it's a real challenge. The problem is, if you think about, I'm going to go back a couple slides on you. So this is kind of the takeoff on the lightweight ROO design, and the idea on this is that it's its own reentry vehicle. So, you know, the ROO is somewhere on a spacecraft. You know, they scatter them around to keep the electronics warm. And so, in the event of a launch accident or a reentry, you know, the spacecraft burns up, and these things free release, and they're their own reentry vehicle. And so, the terminal velocity of these things is about 50 meters a second, but they don't weigh much. So, you know, from an impact perspective, there's just not a lot of energy that you need to dissipate. You know, you've got a 3D carbon-carbon composite material. You've got some pyrolytic graphite here that during the reentry, so you don't overheat your encapsulation layers. Well, with this idea, you know, the terminal velocity of one of these capsules, if you had 4, one of them, if you had a same kind of arrangement where you got the reentry material around the capsule, it's around 125 meters per second. And it turns out that it's not survivable. And so you're like, well, I'll just add more mass to give this thing more beef so that it can survive impact. Well, now you've made it heavier. And now you made the impact velocity faster. And so it's diminishing returns. So the only way you can figure out how to make this thing survive is you make it its own reentry vehicle. Right? So that it separates from the spacecraft. It has its own integral heat shield. It kind of, think of it like the Apollo capsule. It essentially is self-orienting. So in the event that, you know, the computers failed and everything, the Apollo capsule, once it started its reentry, it's aerodynamically set up so that it'll align properly, and the heat shield will be in the right orientation to deflect, you know, all of that plasma during the reentry burn. Well, we're kind of approaching the same concept, and of course we're not going to invent anything new if the Apollo heat shield worked. So our designs are based off of the Apollo heat shield, and this thing becomes its own reentry vehicle. Yes, we have some of the 3D carbon-carbon composite materials on the inside of it, which you can't really see because it's all about the IP thing that no one wants you to see. And then you can see here it's a phantom wall of a spacecraft and how that thing gets integrated in, and the heat shield essentially is on the outside and the rest of it is on the inside, and it's designed to free release as a unit. And so what turns out is that what I didn't know at the time, when we started down this kind of road, was that the Apollo heat shield, you know, when it lands in water, you know, it's designed to absorb some of that impact shock, because, you know, the humans are the most fragile thing on the inside. Yes, you have parachutes, but it's still dropping at a pretty good clip. And So it's basically you have an ablative honeycomb structure on the outside, you have a substrate, and then you have a honeycomb structure on the inside between essentially the heat shield and the RTG, and that's going to absorb some of the impact energy. And then, therefore, whatever you translate to those capsules that really aren't self-sustaining from a survivability perspective, will be able to survive the impact from terminal velocity. See, is there anything else? Oh, and so right now what we're working with in our RTG concept, same as the Brits, is bismuth telluride. It's easy, commercially available, it's low cost, but there's also looking at how do we integrate into the idea, not necessarily this design, but into this kind of design concept. How do you integrate the Stirling engine into it? Either with strontium-90 or some other type of isotope material like americium-241. So in a nutshell, that's kind of where we're at with RPS technology. So it really hasn't gone that far, right? So it's we're kind of going back to the future with the next gen RTG. With MMRTG is essentially a lower efficiency technology from the 1960s from silicon germanium that was developed in the same time frame. Yes, there are other materials out there, such as the lanthanum tellurides, that are really kind of, they show promise, but we're probably a decade away from ever demonstrating some sort of flight capability with those materials. The Brits are really working on some stuff for their space systems, and then of course I think I'm a little biased, but I think the more exciting thing is the commercial piece of it. It offers an opportunity to really demonstrate new ideas, new concepts, and I will say this, that at least the discussions that we've had with NASA and what they've seen of some of the stuff that we've presented, they've been really excited about it, because I think it gets them away from being dependent upon DOE for RPS systems, and then they can treat it kind of like what I was saying earlier, kind of like the water bottle. Well, you just get me a 10-watt RTG and put it on the moon. I don't care how you get it there. I don't care what it looks like. It just needs to be safe and survive and function. So with that, I'll open it up to any questions you've got. Hey, Paul.
How much americium are you talking about?
How much?
How much?
Well, right now the Brits are talking 200 thermal watts, and I think you're talking about 1 watt per gram, so about 2 kilograms. So it's not it's a lot of fuel from a mass perspective, but it's not a lot of fuel from a thermal perspective. So I take that back. It's about 0.1 watt per gram. It's not 1 watt per gram. It's 0.1 watt per gram. And then the strontium-90, believe it or not, is a tenth of that. Just to put it in perspective, just because it's old fuel. If you had new fuel, new strontium-90, you would be in like gangbusters. The company that I've been working with has a patent out on some ways to package the material to reduce the Bremsstrahlung generation, not to attenuate it, but just to mitigate some of the production of it. So it makes it a little bit more user-friendly. It's still not user-friendly, but more user-friendly. But so, yeah, the isotope thing is tricky because in the United States we don't have the ability to reprocess fuel. So you're forced to either build a reprocessing technology from scratch, which is, I think, in my personal opinion, is going to be like moving heaven and earth to get something like that done. It'd have to be like a Manhattan-style project. Or you have to buy it from the French. The Swedes have a reprocessing facility called Studsvik. The Brits have a reprocessing facility at NNL. And then the Canadians are always kind of floating around. They're talking about making plutonium-238 with neptunium. They've got those reactors, what are those things called? CANDUs. Yeah. And those are really amazing things, and I think there's a lot of opportunity there, but if you're working on a DOE contract, there's really not much interest in looking for sources outside the United States. But if you're looking for a space mission, then I don't think NASA has the same kind of restrictions. Did that answer your question, Paul?
Are there any other questions?
You talk a little bit about encapsulation. First, remind us exactly what that is, what it's used for. On your last 2 or 3 slides, you specifically made a line item that we're using tantalum 10 tungsten,
Yeah.
platinum 30 rhodium, platinum 10 rhodium. Why is that? Why, to the cognoscenti, is that an important thing for you to say compared to what was used before? Talk about that a little bit.
So on the lightweight ruse, that was platinum 30 rhodium, and and part of that was that having the ductility necessary during impact or a launch accident, and so the platinum 30 rhodium was a well-characterized material. It's not a standard production material like Teledyne Hua Chang makes platinum 10, platinum 20, but platinum 30, which is what we use in our space program, is a special run alloy. And so when you start thinking cost, especially with the price of rhodium, it gets really expensive. So what the Brits tried to do is figure out what's the least amount of rhodium they could use to have essentially the characteristics they needed upon impact to make sure that it bends, doesn't break. Because the last thing you want to do is have a breach in your encapsulation layer and have the radioisotope actually escape into the environment, into the biosphere. So that's kind of the big difference between the 30, 20, and the 10.
So these are just issues related to getting the alloy that is at an acceptable price, that performs the way you need it. And
Yep.
it happens to be, these are samples of the kind of material.
Yeah, so one of the things with tantalum 10 tungsten, when we started working with this commercial company, they were using tungsten. Tungsten's really brittle, it's really hard, and so if you think of it from a survivability perspective, it's not very good. It's difficult to machine, it's all of these things, and so I suggested, I'm like, well, why are you using that? Why don't you use tantalum 10 tungsten? It's a commercially available alloy. It has essentially very similar shielding properties. You take a little bit of a hit, but it's like a 1 or 2% hit. And the material's more ductile, easier to machine, and like I said, it's commercially available, but it's still not inexpensive. We purchased a rod that's 3 inches in diameter and 36 inches long, and it was $130,000.
Of that.
Yeah, for that.
What does your nomenclature mean? Is that 10% tungsten?
Correct. Yeah, 10 weight percent.
Weight percent. Thank you.
Oh, you're welcome.
Any other
Not
questions?
done yet.
Oh,
Oh, you're not done yet.
Shoot.
Several times you used what sounded like the word rope. What were you talking about?
row?
Roof.
Rue. Oh, I'm sorry. Yeah, so it's a lightweight radioisotope heater unit. So RU is just a short acronym for RHU, radioisotope heater
right,
unit.
fine.
And so the RUs were, I'm sorry, the RUs are, were just, they're 1 watt thermal heat sources just to keep electronics
Sounds
warm
familiar
in
to
the
me.
spacecraft. I think Cassini had,
Yes.
Cassini had 120 or so RUs or something in it. I can't
A
remember.
lot
off
of
the-
numbers spread over to keep that.
Yeah.
Okay. Thank you.
Yeah, you're welcome.
I'm done now.
Okay. Now, one of the things about power, you're talking 10 watts electric.
Yeah.
I mean, that would light a 10 watt bulb, right? I mean, that's sufficient power. If sort of 140 watt, you could light a 100 watt bulb, but not a 150 watt bulb, right?
So yeah, it's
not a lot of power.
Not a lot of power, but a lot of times they'll combine these small power systems with, say, a solar.
Yeah.
So I don't know if you remember the European Space Agency. It's before COVID. COVID makes me, I lose track of how many years things are. COVID's kind of been a big blind spot for me. So it was pre-COVID, probably 2018. European Space Agency landed this solar-powered spacecraft on an asteroid. I don't know if you guys remember that.
Yeah.
And so basically, it would get close, and then it kind of harpooned itself in, and then reeled itself into the surface, and then landed. And it, everyone's like, "Hey!" And it was, NASA was there, everyone was there. They're all glad handing each other, and then it kind of moved and fell into the shadows. And it was like a $5 billion mission.
That was on the Comet.
Was it on a comet?
Yeah, it was on the Comet.
Was that on a comet?
Yeah.
Lights out.
It fell over, just gone.
Yeah, lights out. So I think after that, that's when the European Space Agency, they always had been, we started working with the University of Leicester in 2013. So in the background, they had always been developing an RTG concept, but they had, we'll just throw some money at it. And you saw, this is, I'm going to go back here. you know, this was one of their earlier concepts, and this is one of their later concepts. They've matured quite a lot, and so they would, since 2013, they've been working. But once that happened, it was game on. They're like, we're not going to let this happen again. So if you have just a little 10-watt RTG and you have some solar with it, you have kind of a hybrid system. So you could theoretically probably have 20 watts or something like that. But if you fell into the shadows, or maybe there was an eclipse or something like that, you know, it's not mission over.
You still got 10 or half or some
You
percent.
got something. Yeah.
Charge up batteries.
Right, you charge the batteries back up. And you may take the mission duration a little bit longer because you got to recharge that battery. Maybe instead of having 20 watts, you only have 10, but you're not dead. So.
All right.
Was there, are you guys at UDI doing any Sterling work? Are you working with SunPower or anybody? Or you can't tell me.
Well, I'm going out to SunPower Friday. So that may answer your question a little bit.
Yeah. Well, they're close. I mean, they're close.
So the other thing we're doing is, you know, these SunPower guys, they've been around for a long time, and so one of those converters isn't cheap.
Yeah.
And if you think it from a commercial perspective, obviously, you know, the thing that makes, you know, SpaceX so wonderful, you know, they reuse their boosters, right? They come back down, they reuse them multiple times. And it's something NASA would have never thought of, at least in my opinion. Too risky, right? But
Von Braun did.
But yeah, but this thing is expensive, right? So I'm like, well, back to that analogy I said, you know, Ferrari versus Vega, right? What if we just got a cryo cooler and figured out how to run it back, a commercial one, run it backwards? You may not get, you know, the Ferrari performance, but you'll get something out of it. And it's going to be more than what you're going to get out of Bismuth Telluride. So that's one of the little things we're working in the background is, you know, can we take some commercial cryo coolers and figure out how to operate them in such a way that we get something back out the other end.
But the temperature differentials are different, materials are different.
Yeah, yeah, and so I'm not saying it's...
There are always details, right?
Yeah, I'm not saying it's easy, but I got some really smart guys working with me now. It's amazing. They are the next generation, and some of these kids, of course, one of them is the same age I was when I started here at Mound, and the other one's a little bit older, but, you know, in my mind now they're all kids, right? But
Kenton Sherrick?
Hmm?
Kenton Sherrick?
Yeah.
He called me the other day about something.
He's one of my whiz kids. I love that guy.
He called me the other day about the impact test. I'm the guy he called.
Oh, yeah. So I've got these guys working for me. They're absolutely spectacular, and I'm convinced that, you know, and of course we have. I would like to think a culture that is very consistent with the culture we had here at Mound. So I'm convinced we're unstoppable. Whether or not we are or not remains to be seen, but I really feel good about where we're at and where we're going. And yeah, some of these like, you know, these designs are Kenton Sherrick and his colleague Matt Johnson. So, I mean, I may be the guy behind the green curtain, you know, and I'm coming up with big ideas, but they're the ones that are actually making, you know, designing the hardware, and they're doing a wonderful job.
Yeah, he worked for me down in Cincinnati. He said he's going to UDI. I said, you go. I reached up there and pulled the black and yellow handle for him, and out he went.
All right. Thank you, by the way.
I'm done.
Thank you, Chad.
And cheers.